Section 21.6 Understanding Trends in the Periodic Table from Hartree-Fock Calculations. So if you look at the periodic table, there's a trend from bottom left to top right. Francium has the lowest ionization energy, the lowest electron affinity, and the lowest electronegativity. Fluorine has the highest ionization energy, the highest electronegativity, and the second highest electron affinity. Chlorine has the highest electron affinity. And if you look further, helium has the highest ionization energy. However, helium has a negative electron affinity because helium does not like to accept one additional electron. Now let's look at the Hartree-Fock calculations and what Hartree-Fock calculations can do for us. We can calculate the energy of the highest occupied atomic orbital for all those elements. And it turns out the energy of the highest occupied atomic orbital of these elements is roughly negative the ionization energy. Well, that's understandable. The ionization energy is the amount of energy that's required to remove an electron from the atom. So let's look at lithium as an example. Ionization energy is the amount of energy required to remove the electron in the 2s orbital in the lithium atom. Well, if you think about this, how much energy is required to remove this electron? Well, it's simply the ionization energy, right? But also, it's the difference between 0 and the atomic orbital energy of this 2s electron. So really, the energy difference is the absolute value of the energy of the 2s orbital. And therefore, the energy of the 2s orbital or the 2s electron in the lithium atom is negative ionization energy. So again, you can use the Hartree-Fock self-consistent field method to calculate the atomic orbital energy, and that's simply negative ionization energy. I want to show you a graph here. This is a negative Hartree-Fock atomic orbital energy, and this is the ionization energy. And you see a perfect, nearly perfect match. Now let's talk about electronegativity. Molekim proposed at least a couple equations to calculate the electronegativity. So one equation is the electronegativity is equal to a constant times the sum of ionization energy and electron affinity. This is another equation he proposed. He proposed to add another constant here. So again, Molekim proposed a couple equations to connect the electronegativity chi to the sum of ionization energy and electron affinity. So now you can see if you have a higher ionization energy and higher electron affinity, you have a higher electronegativity. All right. So, and if you have the lowest ionization energy and the lowest electron affinity for francium, well, of course, this element, francium, has the lowest electronegativity. These two are the definitions of the ionization energy and electron affinity. You learn this in general chemistry. But in some general chemistry textbooks, the definition of electron affinity is wrong. The correct definition is this: the amount of energy released when the atom is getting an electron. Okay, the amount of energy released when the element is getting an electron. So, for example, the electron affinity of fluorine is positive because when the fluorine atom gets an electron, energy is released. Fluorine minus has lower energy than the neutral fluorine atom. However, in some general chemistry textbooks, the definition of this electron affinity is the opposite. And then they have a negative electron affinity for fluorine, and that's wrong. Linus Pauling has some other equations to define electronegativity, and also an equation to determine the difference in electron negativity. Okay, over here. This E sub D is the so-called dissociation energy, and AB is a diatomic molecule, so this is just the dissociation energy between this AB bond, and this is between AA, this is between BB. All right. So what does this equation tell you? Qualitatively, it tells you if the electron negativity of A is very different from B, and then you will see a stronger bond between A and B than the average of the bond energy between A and A and B and B. All right. So again, if the two elements differ significantly in electron negativity, they have more ionic character, and the bond strength is greater. Pauling has a couple formulas to estimate the bond energy for a heteronuclear diatomic molecule using the electron negativity difference. So this too. They share something in common. This part is in common. And if you look at this, if chi A differs significantly from chi B, you'll have a larger bond energy due to the higher ionic character. And over here, he used arithmetic mean of this AA bond energy and BB bond energy. This is called geometric mean of the bond energies of AA and BB. So he proposed both equations. The second equation is often slightly more accurate than the first one. And if you wonder what this 23 means, actually this 23 happens to be the numerical value of kcal per mole. That's equal to 1 electron volt. Over here, this is the conversion from electron volt to joule to kilojoule per mole and two wave numbers. In case you're interested in this, but it just doesn't matter. So this 23 can be easily memorized. If you know 1 electron volt, that's roughly 23 kcal per mole. Now let's look at a very important process in chemistry. It's so-called electron transfer. And when A electron transfers from A to B, A is oxidized, B is reduced. So this is a very important process in the oxidation-reduction reaction. And when does this kind of oxidation reduction reaction happens easily? Well, if you have an atom with a very low ionization energy, that means a very little energy is required to remove this electron. Okay, and then if you have a very large electron affinity in the other atom, for the other atom, and then electron transfer is easy. So that means if you remove an electron from A, it requires very little energy. And then if you give the electron to B, a lot of energy is released. Right? So overall, if A has a low ionization energy and B has a very large electron affinity, and then the electron transfer from A to B is easy. Now let me give you another example. A is potassium, B is fluorine. So it's really easy to remove electron from a potassium atom. And then this electron can be given to the fluorine atom to form fluorine minus. A lot of energy is released. Alright, so that makes the electron transfer from potassium to fluorine easier than some other transfer between some other atoms. Finally, let's look at the ranking, the energy ranking of the atomic orbital energies. Alright, so you just need to write out n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, etc. And then you draw arrows with a 45 degrees angle to the horizontal line. So there's arrows. And then you follow these arrows to fill in this atomic orbitals. So 1s first, and then 2s, and then 2p, 3s, and then 3p. After 3p, it's 4s. And after 4s, it's 3d. And then 4p, 5s, and then 4d, 5p, 6s. And then 4f, 5d, 6p, and 7s. So now you can tell you're filling 6s orbital before filling this 4f orbital. So it's not just the value of the principal quantum number n, but also the angular momentum quantum number L that determine the relative energy ranking of these atomic orbitals.